I am Dr. V. Janaki, Assistant Professor, PG and Research Department of Chemistry, Sri Sharada College for Women, Salem 60. In this content, we will see what is meant by the ionic bond and conditions for the formation and what are the factors governing the formation and the characteristics of ionic compounds. In addition to that, we will see what is meant by the lattice energy, how we can determine by using Born-Haber cycle. First one, let us see what is meant by the chemical bonds. The chemical bond is defined as a force that is acting between two or more atoms so that it can hold them together and forms a stable molecule. So there are three different types of bonds are there. The first one is ionic or electrovalent bond. The second one is covalent bond and the third one is coordinate covalent bond. And there will be a fourth type of bond is there. It is called metallic bond. Here, let us see what is meant by the ionic bond. An ionic bond is a type of a chemical bond formed through the transfer of electrons from one atom to the another. Here, let us consider an atom A has only one electron in the valence shell, and the another atom B which has 7 electrons in the valence shell. A has 1 electron in excess and B has 1 electron short than the stable atom. Therefore, A can transfer an electron to B. In this transaction, both the atoms acquires a stable electron octet and results in the formation of positive ion called as cation and the negative ion called as anion. And these ions are held together by electrostatic attractions. The electrostatic attraction between these positively charged cations and negatively charged anions are produced by the electron transfer, and it constitutes the ionic bond, or we can say it is an electrovalent bond. The compound containing such a bonds are called as ionic compounds or electrovalent compounds. Now let us see what are the conditions for the formation of ionic bond. The first one is the number of valence electron. Suppose if the ionic bond is formed between A and B, the atom A should possess 1, 2 or 3 valence electrons, while the atom B should have 5, 6 or 7 valence electrons. The elements of group 1A, 2A and 3A satisfy these conditions for atom A, and those of a groups 5A, 6A and 7A satisfy these conditions for atom B. The second one is the net lowering of energy. To form a stable ionic compound, there must be a net lowering of energy. That is, the energy must be released as a result of electron transfer in the formation of ionic compound. The first one, the removal of electrons from sodium atom. It requires input of energy, which is called ionization energy. It should be very low. The addition of an electron to Cl, it releases some energy which is nothing but electron affinity. It should be very high. The third one, the electrostatic attraction between the Na plus and Cl minus in the solid compound should be high. So these are the values for the ionization energy, electron affinity values and the formation of Na plus and Cl minus. Suppose if we calculate the net energy released in the above step by adding 187 plus 85 and minus 119, that is equal to 153 kilocalories. Here, since the overall process results in the lowering of energy during the formation of NaCl. Now let us see what are the various factors governing the formation of ionic compound. The first one is ionization energy. Lower the ionization energy, greater will be the tendency of the metal atom to change into cation and hence greater will be the ease of formation of ionic compound. That is why the alkali metals and alkaline earth metals form ionic bonds easily. Out of these two, the alkali metals form ionic bonds easily as compared to alkaline earth metals. In a group, the ionization energy decreases as we move down the group, and therefore the tendency to form ionic compound increases in a group. It is also downwards. For this reason, the cesium is the most electropositive atoms among the alkali metals. The next one is electron affinity. The atoms which accepts the electrons and changes into anion. It should be high. Higher the electron affinity, more is the energy released and stable will be the anions form. The elements of 6A and 7A have in general have higher electron affinity and have higher tendency to form ionic compounds. Out of these two, the elements of 7A, that is halogens, are more prone to the formation of ionic bond than the elements of 6A. In moving down the group, the electron affinity decreases and therefore the tendency to form ionic bond also gets decreases. The third one is lattice energy. After the formation of the cations and anions separately, they have to combine to form ionic compounds. During this process, the energy is released. It is called lattice energy. It may be defined as the amount of energy released when 1 mole of ionic compound is formed from its cations and anions. Greater the lattice energy, greater will be the strength of ionic bond. The value of lattice energy depends on two factors. The first one is the size of the ions. The second one is charge on the ions. The first one, size of the ions. In order to have the greater force of attractions between the cations and anions, their size should be small, as the force of attraction is inversely proportional to the square of distances between them. The next one is the charge on ions. Greater the charge on ions, greater will be the force of attractions between them, and therefore greater will be the strength of ionic bonds. Now let us see some examples of ionic compounds. A simple sodium chloride molecule is formed from an atom of sodium and one atom of chlorine. Here sodium has 1 electrons while Cl has 7 valence electrons. Sodium transfers its electrons to Cl and both achieve a stable electron octet. Thus, Na gives Na plus and Cl gives Cl minus, and the two ions are joined together and forms the ionic bond. Here, this ionic compounds will exist as crystals. The positive and negative ions attract each other with the electrostatic force that extends in all the directions. This means that ions will be bonded to a number of oppositely charged ions around them. Therefore, in solid state, single ionic molecules do not exist as such. Rather, many positive and negative ions are arranged systematically in an alternating cation-anion pattern called crystal lattice. In the crystal lattice of NaCl, we can notice that there will be a large number of Na plus and Cl minus ions are arranged in an orderly manner so as to form a cubic crystal lattice. Each Na plus is surrounded by 6 Cl minus and each Cl minus is surrounded by 6 Na plus. This makes a network of Na plus and Cl minus ions which are tightly held together by electrostatic force of attraction between them. Now let us see one more examples here, magnesium chloride. Magnesium has 2 valence electrons while the chlorine has 7. The magnesium transfer its 2 electrons, one to each chlorine atom, and thus all the 3 atoms achieve the stable octet. In this way, the magnesium atom gives and forms Mg2 plus ions, and the 2 Cl atoms forms the MgCl2 compound. The next example is calcium oxide. Calcium has 2 valence electrons while oxygen has 6. The calcium atom transfers its 2 electrons to the same oxygen atom. Thus both calcium and O achieve the stable electron octet, forming Ca2 plus and O2 minus ion. Thus, the alkyne molecule has calcium oxide has Ca2 plus and O2 minus. Now let us see what are all the characteristics of ionic compounds. Here the ionic compounds are made up of positive and negative ions which are held together by electrostatic force in a crystal lattice. Each ion is surrounded by opposite ions in an alternate position in a definite order in all the directions. The first one, solids at room temperatures. Account of strong electrostatic forces between the opposite ions, these ions are locked in their allotted positions in the crystal lattice. Since they lack the freedom of movement, which is the characteristics of the liquid state, they are all solids at room temperatures. The second one is high melting points. Ionic compounds have high melting points since the positive and negative ions are tightly held in their position in the lattice. Only at higher temperature, the ions have sufficient kinetic energy to overcome their forces and attain the freedom of movement as in a liquid. Thus, the ionic compounds needs heating to a higher temperature before melting. The third one is hard and brittle. The crystals of ionic substances are hard and brittle. Their hardness is due to the strong electrostatic forces which hold each ion in their allotted position. And the next one is soluble in water. When a crystal of ionic substances is placed in water, the polar water molecules detach the positive and negative ion from the crystal lattice by their electrostatic pull. These ions then get surrounded by water molecules and can lead to the independent existence and thus dissolved in water. And the next one is conductors of electricity. Solid ionic compounds are poor conductors of electricity because the ions are fixed rigidly in their positions. In the molten state and in the water solutions, the ions are free to move. Thus, the molten ionic compounds or in their aqueous solutions, they conduct a current when placed in an electrolytic cell. And the next one is they do not exhibit isomerism. The ionic compounds involving electrostatic lines of force between the opposite ions is not rigid and non-directional. So therefore, it is incapable of exhibiting stereoisomerism. And the next one, the ionic reactions are fast. The ionic compounds generally give reactions between ions, and these are very fast. Now let us see what is meant by the lattice energy. The positive and negative ions in an ionic crystals are held together by the electrostatic forces, which is called lattice energy. This lattice energy can be determined by using the Born-Haber cycle. And this is the Born-Haber cycle for the ionic compound NaCl. In the first step, the sodium, which is present in the solid state, gets converted into gaseous state by the process of sublimation. And in the step 2, the sodium, which is present in the gaseous state, gets converted into Na plus ions. So it needs energy that is called ionization energy. And similarly, the Cl2 gas, which gets dissociated into Cl gas by the process of dissociation. And then the Cl gas gets converted into Cl minus ion by the electron affinity. So there will be a formation of this Na plus and Cl minus ion. So these Na plus and Cl minus are held together by the electrostatic forces, which is nothing but lattice energy, which is represented by the symbol U, and it results in the formation of NaCl ionic compound. Now, let us see what are all the various steps involved in the determination of lattice energy. The first step is the conversion of metallic sodium into gaseous sodium atoms by the process of sublimation energy. The step 2 is the dissociation of gaseous chlorine molecules into gaseous chlorine atoms, and this is called dissociation energy. And then the step 3 is the conversion of gaseous sodium atoms into sodium ions. The amount of energy required to convert 1 mole of gaseous sodium atoms into sodium ions in the gaseous state is called ionization energy. And then the fourth step is the conversion of gaseous chlorine atoms into chloride ions. The amount of energy released when 1 mole of gaseous chlorine atoms are converted into chloride ions in the gaseous state is called electron affinity. And then the final step is the combination of gaseous ions, that is Na plus and Cl minus ions, to form NaCl crystals. The amount of energy released when 1 mole of solid crystalline compound is formed from the gaseous ions of opposite charges, that is Na plus and Cl minus, is called lattice energy. The lattice energy can be calculated by using the Hess's law. Here, Hess's law, delta HF is equal to, which is nothing but the enthalpy of formation is equal to sublimation plus dissociation plus ionization energy plus electron affinity plus U. So here the sublimation values, dissociation values and ionization values, electron affinity and enthalpy values are given. By we can substituting the above various values in the above equations, we will get U is equal to minus 758 kilojoule per mole. By using this formula, we can calculate the lattice energy of any ionic compounds. Thank you.